Hello everyone. Welcome to GPU Teaching Kit Module 14, Efficient Host Device Data Transfer. We are at lecture 14.1, Pinned Host Memory. The objective of this lecture is for students to learn the important concepts involved in copying data or transferring data between host and device in CUDA programming. These two important concepts are one, the direct memory access or DMA hardware, two, uh, the concept of pinned memory in virtual memory management. When we call a CUDA main copy function in the CUDA host code, the function is actually implemented with a piece of hardware called direct memory access or DMA. Rather than executing instructions to load data from the CPU memory and write into the GPU global memory during a transfer from CPU to GPU, it actually uses the DMA device to keep reading from the CPU memory and writing into the GPU global memory. This is illustrated with the picture on the slide where we show the CPU main memory on top of the picture and the GPU global memory in the bottom of the picture. And we show that the DMA is a device that sits in between and the read data from one memory and write data into another memory. There's a few reasons why we use a special hardware. The first reason is we oftentimes need to copy quite a bit of data from CPU to GPU and from GPU to CPU. So when we copy a large amount of data, this can take a while. So using a special piece of hardware allows the CPU to actually go and execute other tasks when the data transfer is being done. This increases the overall productivity of the system. The second one is that we can design this DMA as a specialized, highly optimized hardware to transfer a number of bytes requested by the operating system. And this could be a very simple piece of hardware, but highly optimized with a counter that counts down the number of bytes that still need to be transferred, and then a very efficient addressing mechanism to to be able to access one memory and write into another memory. Keep in mind that this transfer is between physical memory address space regions, and in some cases, the memory involved in the transfer could even be some memory mapped I/O in the in the GPU card or I/O cards. The transfer typically goes across a system interconnect, and most of the systems today is the PCI Express or PCIe that we have already covered in a previous lecture. In order to understand the performance behavior of CUDA main copy, we actually need to understand a little bit more about virtual memory management in modern computers. In these computers, when we have virtual memory management, many virtual memory spaces could be mapped into a single physical memory. Each process will have its own virtual memory space. And when we run many processors on the same system, the virtual memory spaces, or sometimes we call the virtual address spaces, can be mapped into a single physical memory. And all these processes will be sharing the locations of a single physical memory. These virtual addresses, essentially the pointer values that we use in the program, are translated into physical addresses. In practice, not all the variables and data structures are always in the physical memory. Each virtual address space is divided into pages, and these pages are mapped in and out of the physical memory. Only the most frequently used pages will be used in the mapped into the physical memory. So some of the virtual memory pages can be mapped out of the physical memory to make room for the virtual pages of other processes or even the virtual pages of the same process. So whether or not a variable is the physical memory is checked at address translation time. And whenever we access a variable through a pointer, the computer hardware actually checks whether the page uh, that contains that variable is mapped in or out of the virtual address space during the address translation time. And this concept affects the behavior and the requirements of data transfer. Remember, we're using a DMA hardware, and the DMA hardware uses physical addresses. So when the CUDA main copy needs to copy a section of the array or an entire array, it is implemented as one or more DMA transfers. And in order to perform this transfer, uh, the, the CPU needs to first translate the address into from virtual address into physical address and check the presence of the pages involved in the source and destination regions. Keep in mind that when we transfer a big chunk of data from the source region, let's say from the CPU source region to the GPU destination region, can involve multiple pages. So we need to be able to check the presence of these pages in the physical memory. In order to achieve high efficiency, we will be checking the presence of all the pages involving a transfer at the beginning of the transfer. And we're not going to do any additional address translation for the rest of the transfer so that we can achieve very high efficiency and speed once the transfer starts. Since we can be transferring a large chunk of data, it could take a while. During this time, the operating system could accidentally page out one of the pages or one or more of pages of the data. So if this happens, this can cause a serious problem because that page is being read or written by the DMA. And especially when the operating system paging another page, virtual address, into the same physical page, then the read and write to involved in paging in the other page can conflict and essentially corrupt the data that is being transferred to the GPU or from the GPU. So this leads to the concept of pinned memory used in DMA data transfer. In order to avoid the problem of one of the pages involving the transfer being paged in and out during the process, we require that the DMA use what we call the pinned memory. And these pinned memory are the virtual memory pages that are specially marked so that they cannot be paged out of the physical memory. They will always stay in that physical memory page until it's unpinned. So we can allocate memory by requesting a pinned memory. So when we do a memory allocation with malloc, there's a special form of malloc that will allow us to allocate a chunk of memory that are pinned in the physical memory. And these pinned physical memory, pinned virtual memory pages are also called page locked memory or locked pages in the literature. So whenever we have a CPU memory region that serves as the source or destination of a DMA transfer, that is, when we give an address to the DMA and transfer a chunk of data starting from the address, the memory that is involved in the transfer must be allocated as pinned memory. More specifically, when we call CUDA main copy, when the CUDA main copy calls the DMA use requires that any source or destination in the host memory is allocated as pinned memory. However, if the application code did not allocate the memory as pinned memory, but use a unpinned memory to call CUDA main copy, then the implementation of CUDA main copy will first copy the data into the pinned memory, and this creates an extra overhead. So that's why the CUDA main copy function runs faster if the host memory source or destination is allocated in pinned memory, since there's going to be no extra copy involved when executing the DMA. So this leads to the question, how do we allocate a free pin memory? Instead of using the cmalloc function, we can use CUDA host alloc in the host code with 3 parameters to allocate pin memory. The first parameter is the address of the pointer to the allocated memory. This is the same as malloc. And the second one is the size of the allocated memory in bytes, also the same as malloc. But the third one is an option, and we typically use CUDA host alloc default. And if for those of you who are interested in more sophisticated usage, you can refer to the CUDA programming guide. When we're done with a piece of pin memory, we can free it with CUDA free host. And it only takes one parameter, which is the pointer to the memory to be freed. Now that we know how to allocate pin memory in a CUDA program, we now look at how we can actually use the pin memory. We use the allocated pin memory and its pointer in exactly the same way as those returned by the cmalloc functions. The only difference is the allocated memory cannot be paged in or out by the operating system. And this makes it much more efficient when we use the allocated pin memory as the source or destination of CUDA main copy. And this makes the CUDA main copy function run twice as fast. And the pin memory is a limited resource. So someone may say, okay, since the pin memory will make the CUDA main copy run twice as fast, I can just allocate all my CUDA host memory variables as pinned memory. Unfortunately, if we do so, we can overutilize the pin memory, and pin memory is a very limited resource in any computing system. And if we overuse pin memory in an application, it may actually cause serious performance degradation for other programs, and or in some cases even for itself, because it may not even have enough physical memory that can serve to host all the virtual pages so that essentially the system can become extremely slow. This slide shows the usage of pin memory in the vector addition example. When we allocate the input vectors A and B in the host memory, we can use CUDA host alloc to allocate memory for these arrays. And once we allocated these arrays as pin memory, we can just call CUDA main copy to copy A and B from host memory to the device memory. And these copies should now run twice as fast. Completes lecture 14.1. Thank you.